this is the problem that I worked on during my master thesis, and later it led to 2 papers, which is joint research with Rajesh Kannan and Shivaram Krishna Pragada. Rajesh Kannan was my thesis advisor, and Shivaram is one of his students. Now they are at different places. So let me first give discuss what this problem is, and also discuss what we did in this work. So recall a graph is set of vertices with set of edges. Set of edges is basically unordered pairs of vertices such that these vertices are different. And if you have a vertex set which is labeled, you could associate an adjacency matrix whose ijth entry is 1 if the corresponding vertices form an edge and 0 otherwise. And we'll call the set of eigenvalues of this matrix as the spectrum of the graph. And we say 2 graphs are cospectral if they have the same spectrum. So next, there's an equivalent definition for graphs to be cospectral, and that happens when you could produce an orthogonal matrix, which is a similarity matrix between the adjacency matrices of the graphs. So there is also a definition for graph isomorphism in terms of matrices. And 2 graphs are isomorphic if the similarity matrix is the permutation matrix. So it's clear that permutation matrices are orthogonal. So graph isomorphism implies graph cospectrality. And then we could think about the converse, but that's not true. The first example was given by Kolaj and Singovich, and here is the smallest example of cospectral non-isomorphic graphs. This was given by Svetkovic. So here are 2 graphs on 5 vertices, and they have the same spectrum. Clearly, they are non-isomorphic. And I should also mention a connection with the famous old paper, Can One Hear the Shape of a Drum? Basically, it's the same problem. If you have 2 drums that sound the same, can you conclude that they have the same shape? So later, Fisher modeled the shape of the drum by a graph. So that is the problem equivalent to constructions of cospectral non-isomorphic graphs. And we say graph is determined by the spectrum, or DS for short, if any other graph which is cospectral to it is also isomorphic. So basically, DS graphs can be recovered using the spectrum, and DS graphs are identified uniquely with that spectrum. And Havers recently conjectured that almost all graphs are DS. What that means is that if you look at the ratio of DS graphs on n vertices with the total number of graphs, that ratio tends to 1. So if n is large enough, you pick a graph randomly, it's more likely that it would be DS. And since almost all graphs are DS, for almost all graphs, this graph isomorphism problem is same as checking whether they have the same eigenvalues, because DS graphs are identified uniquely with the spectrum, right? And recently, it was shown that almost all graphs are determined by their eigenvalues and angles by V. Irwin, Fulbrook, Kobler, and Verbitsky. One thing to note is it's a weaker statement than this conjecture. Eigenvalues are basically the cosines of standard basis vectors that the angles between standard basis vectors and the eigenspaces of the eigenvalues. So if you are given a graph, you could ask this question, is it DS? But it's usually hard to show that it's a DS graph, and very few graphs have been shown to be DS. So instead, you could try to show it's not DS, and which is easier. You just produce an example of cospectral non-isomorphic graph. And there are many methods to do this, so I'll discuss one such method that works for bipartite graphs. So here is, so let me recall what bipartite graphs are. A graph is bipartite if you could partition the vertex set into 2 sets, U1 and U2, such that no 2 vertices in that set UI form an edge. And if you have a bipartite graph, the corresponding adjacency matrix has a block matrix form, and it's defined using this matrix B, which is called the biadjacency matrix of the graph. And here is the construction. Consider this bipartite graph on 4 vertices. There are 2 parted sets. I have labeled it red and blue. So imagine, consider the red set and unfold it along the blue set. Imagine opening a notebook, and here is the first graph that we get. And similarly, take the blue set and unfold it along the red one, and you get another set. So here you are creating copies of the same parted set. And I'll call these new graphs as unfoldings of this bipartite graph. And if you relabel these unfoldings, they also have their adjacency matrix also have the nice block matrix form. And it was shown that these unfoldings are cospectral if and only if the matrix B is a square matrix. And that works also for the normalized Laplacian matrix. This was proved by Butler, who also introduced this unfolding construction. And the condition for these graphs to be non-isomorphic was given by G et al. They show that happens when B is not permutationally equivalent to its transpose, and which means there are no 2 permutation matrices P1 and P2 such that P1 B2 is B transpose. In fact, they had proved this result for a more general setup where you could unfold one partition multiple times and unfold both the partitions, parted sets at the same time. And they also simplify the proof for cospectrality of Butler. So they generalized it in one way. There's also another way to generalize it, which is using tensor product of matrices. So consider this adjacency matrix of the first unfolding and partition it into 4 blocks. And look at each block. Each block can be written as tensor product of 2 smaller matrices here. And now I collect the blocks on the left into this 3 cross 3 matrix and blocks on the right into this other matrix. So this was the adjacency matrix of the original bipartite graph. Here the subscript P denotes that I'm taking partition tensor product, which is basically blockwise tensor product. And similarly, you could decompose the adjacency matrix of the second unfolding here. And notice they have the same common factor here. So then the next question is, can you replace this common factor using an arbitrary matrix, adjacency matrix of the bipartite graph, which is given by the matrix V. So if you take V to be 1 cross 2 matrix whose both entries are 1, you get Butler's construction. If you replace it with all ones matrix of size m cross n, that gives you G et al.'s construction. And for the answer for the arbitrary matrix is what I'd worked on, and that led to this paper in discrete math. We give cospectral for the unfoldings to be cospectral and non-isomorphic. We give conditions for graphs to be cospectral and non-isomorphic. And recently we wrote another paper where we deal with the non-bipartite case. We give 3 constructions including multipartite graphs and so on. So basically the takeaway is that unfoldings of bipartite graphs, which I explained using graph theoretic terms, it's basically partition tensor products. And I should also mention one observation that if you look at the union of these unfoldings, they are basically the components of direct product of the 2 bipartite graphs, and that leads to interesting connections with products of graphs. And there are different ways graph products are studied. For example, there is this notion of prime factorization over graphs and so on. So there's an interesting connection we found. And yeah, thank you for your attention.
Thanks to the speaker for finishing before time. So we have time for a few questions.
When you write this graph and its connection as a matrix, so it depends on the rules that you put in, that the matrix can be very complicated. Then how do you show that it is always diagonalizable?
We work with symmetric matrices, right? So symmetric matrices are diagonalizable.
So always you take that. So can't your graphs be complicated enough that it is not a symmetric matrix?
No, because we work with adjacency matrices, those are symmetric, so you could use those facts.
Okay. But it can be more complicated.
There are other matrices you can relate with graphs, for example, a Laplacian matrix, normalized Laplacian matrix, distance matrix, and so on. But there, for Laplacian matrix is positive semi-definite matrix, so there you use those facts about positive semi-definite matrix. Here, you just need to use facts about non-negative symmetric matrices. Okay.
Is there any notion of describing isomorphism for directed graphs by looking at associated spectrum? Because those would be non-symmetric matrices in particular.
Yeah, but that's not what I'd looked on. But maybe you could.
Okay. Is there anything like this in the literature? I do not know.
In literature, I didn't.
You also don't know.
I didn't come across directed graph case.
Okay.
You talk about adjacent matrix and eigenvalues.
Yeah.
Do you worry about eigenvectors? For example, if you take a very simple square lattice with periodic boundary condition, then the adjacent matrix has a structure.
Yeah.
You know the nature of eigenvectors in terms of so-called Bloch's theorems and so on.
Yeah. So in this problem, I didn't come across eigenvectors, but people study eigenvectors as well. Let's say this page rank algorithm, you need to compute eigenvector of a matrix, and that gives you ranking. So there are. So here I mentioned this conjecture. So angles, I said. It's the angle between the standard basis vectors with the eigenspaces. So maybe people also study eigenspaces of graphs and so on. So their eigenvectors might come up.
Because in physics, sometimes these eigenvectors
Yeah.
are very important.
Yeah.
They correspond to some localized states and so on.
Yeah.